Welcome to the Mining and Metallurgical Society of America webinar series. MMSA is an association of senior industry professionals who conduct themselves and their work to the highest standards. The society only accepts applicants who have been educated, trained, and experienced in the mining industry for at least 10 years and who have been referenced by a colleague or industry peers. Once a member, a professional may apply to be a qualified person with the earned expertise in one or more defined professions from specific and extended work in the industry. If you are interested in becoming an MMSA member, be sure to check out our website at mmsa.net for information on the application process.
Hmm.
The Society is dedicated to increasing public awareness and understanding about mining and why mined minerals are essential to modern society and human well-being. The Society concerns itself with fundamental principles and with problems facing the industry in such areas as legislation, economics, and education, as well as environmental concerns, labor relations, and health and safety. Representatives of the Society from time to time testify before legislative bodies and provide advice to federal agencies. The MMSA provides continuous professional development opportunities for its members through these QP webinar series. The series provides subject matter experts lectures on a wide range of mining topics and is presented most months of the year. My name is Kristen Guerin Davey, MMSA member and social media and webinar director. I will be introducing the webinar today. The title of today's webinar is Sifting Through the Tailings by Dr. John Keller, professor at South Dakota School of Mines. Questions can be entered in the chat. The speaker will answer the questions after the presentation is completed. Please turn off your cameras unless you are asking a question. And I'll hand it over to Curtis.
Good afternoon, everyone, and thank you for joining us this afternoon in our continuing webinar series of topics important for our continuous professional development. We're very pleased today to have Dr. John Keller with us. He is a distinguished and Douglas Firstenau Professor of Materials and Metallurgical Engineering at the South Dakota School of Mines and Technology. He has been on the South Dakota Mines faculty since 1990, and in 1994 was selected as a National Science Foundation Presidential Faculty Fellow, and in 2016, a distinguished member of the Society for Mining, Metallurgy, and Exploration, in addition to receiving industry awards for excellence in education. Dr. Keller's research focuses on applied particle technology, particularly interfacial phenomena of froth flotation and the processing of indigenous minerals and mine tailings. We welcome John and look forward to your presentation.
Well, thank you all for taking the time today to listen to the seminar. We'll go ahead and get started. This is kind of the outline. I'm going to try to define tailings and some historical examples, and then go through some options that industry uses to reuse or discard tailings, and then finish it up with some kind of research and thoughts from our lab. So let's go ahead and get started. Tailings are the product of a milling operation, and these numbers are very, I guess you could say, highly estimated, but I found data that says there's estimates of 10 to 14 billion tons of tailings produced annually, and a worldwide inventory of tailings estimated at 282 billion tons. So those are clearly estimates because we've been mining for so long. It would really be hard to get a much better number on that inventory. And the tailings are each unique in their own right because they come from an ore body that has been comminuted. So it's highly dependent upon the type of ore body that will produce a given type of tailings. And one of the commonalities is they are comminuted particles. And I'm going to use these definitions that you see here throughout the presentation. Sand have a range between 2 millimeters to 75 microns, silt being between 75 and 2 microns, and clay being less than 2 micron sized particles. And I note that these ranges are arbitrary and in my opinion, somewhat misleading. These come from more, I guess you could say, the geotechnical side in terms of defining particle sizes. But I say they're somewhat misleading, particularly clay clay to me, as we'll talk about, mean actual clay minerals. But by this definition, any particle less than 2 microns is called a clay, when in fact it might not be a clay mineral. Similarly, sand, to me, that implies quartz, when in fact it may not be quartz. But regardless, those are kind of the standards that have been arrived upon in terms of different particle size uh, of tailings. And mineral grades are continually decreasing, right? We've mined the high grade ores first. That's not to say there's still some coming online, but in general, ore grade decreases, and the size of the desired minerals that you're going to concentrate goes down. They're more finely disseminated within the ore. Consequently, comminution increases, and the tailing size also tend to decrease with time. So we're seeing finer and finer tailings coming online. As I mentioned, the makeup of tailings quite variable, depends upon the ore body, but I've listed some of the minerals that are commonly encountered in tailings: quartz, kaolinite, which is a clay, muscovite, montmorillonite. So it's a mixture of oxides typically, and these kind of sheet silicates or clays are very common. A lot of them are aluminum silicon based, and that'll become important when we start looking at some of these options for uh, discard or reuse of tailings. And of course, within the tailings, there is often a predominant ore mineral type. If you have a porphyry copper deposit, for example, you want to recover the chalcopyrite for the concentrate, leaving behind the gangue minerals such as pyrite or arsenopyrite. With a carbonate ore body, you might want to concentrate dolomite, for example, and leave calcite behind. So it really can be a Duke's mixture of what the mineral types are left with in the tailings themselves. And then there's other categories of tailings, which I call here from a prior large scale ore treatment process that's very specific. For example, fly ash are the minerals that remain after coal combustion. Tremendous amount of fly ash produced because of coal combustion, and they contain primarily silicon, oxygen, or aluminum, iron oxides. Red mud are these oxides that remain after bauxite processing, primarily iron oxide based minerals. And then slag is the glassy amorphous material, generally metal oxides left after smelting and refining. I'm not going to talk any more about red mud, but refer to fly ash and slag a couple times here, in addition to the traditional tailings that one might find from a mineral concentration event. So here I'm thinking about the tailings immediately after milling or producing a concentrate, such as froth flotation. The tailings are usually in an aqueous slurry containing 60 to 80 weight% water. And so there's a need to dewater the tailings, reuse that water, and typically that occurs by thickening, where below we're looking at a traditional rake type thickener. We add flocculants to expedite the sedimentation of the particles. The thickening will reduce the water content to usually less than 50 weight% water. And I note that you're adding a chemical here, and that's a cost that is usually paid simply to expedite the sedimentation and the ability to reuse the water. Now, I was trained as a mineral processor, and this was really the end of the line in terms of our background and processing in the days that I were trained. And we'd go to a tailings pond. It was the end of the story, and we'll see that these days there's a lot more to the story after thickening. And um, historically, those flocculated tailings would be sent to a tailings pond, and their tailings ponds are still used in a lot of operations, especially those that have been operating for a long period of time. They're monitored, the ponds are monitored for leakage, there's liners, there's a lot of environmental and geotechnical consideration around the design of the tailings pond. But this event in 2019 in Brazil, the Brumadinho tailings dam failure, where it's estimated that 12 million metric tons of tailings were released and 270 people died. That really, I think, kind of changed the game in terms of tailings and how we need to uh, better handle them. And other issues around tailings dams, airborne dust, acid mine drainage, if you have sulfide minerals. And so all of those things together really, I think, expedited how we handle and consider tailings today beyond a tailings pond. And so here's kind of a graphic I put together, just trying to show how you might approach this situation. On the left, I'm just calling these new tailings. So this would be a current operation. And assuming that all the minerals of economic value have been recovered, our two options are to dispose of the tailings or to repurpose them into some other product, perhaps. And then on the right are what I'm calling old historical tailings. And I'll show you an example of that here in a minute. This is a mining operation that has ceased operation, and the tailings remain in a tailings pond. One option is to do nothing. Another option might be to reprocess or repurpose those old tailings. And here's an example close to my home in the Black Hills. This is the Grizzly Gulch Tailings Dam just above Leeds, South Dakota. You can see there's the tailings dam would be off in the edge behind here where it's dry, and then there's this water that remains, and these are the tailings, and then there are tailings underneath that water as well. So I said it's called the Grizzly Gulch Dam. Here is a picture on the right, the Grizzly Gulch on what they call Beach One on the water. So these are historical tailings from the former Homestake mine. Tailings were deposited there at Grizzly Gulch from 1977 to 2002 when the mining operation stopped. And it's estimated that Grizzly Gulch contains roughly 440 million tons of tailings. And so this is a site that's managed currently by Barrick Gold. There's no reprocessing going on. There's an engineer assigned to monitor and make sure the tailings dam is secure. And just to go back to this example, when I visited there now 2 years ago, it's a very serene place. It's a locked area. There's elk running around. The water is at about pH 7, so it isn't very acidic. And unless something changes, the dam will remain. I'm told it's highly monitored and safe. But that's a big deposit in the Black Hills of South Dakota. And so that is kind of the do nothing in the do nothing, no reprocessing stage of its life. But one thing to consider with historical tailings such as Grizzly Gulch is over time we're looking at the periodic table of the 1980s, 1990s, 2000s. with time, we use more and more minerals contained by the elements within the periodic table. And so some of the examples going from the blues in the 80s to the greens in the 90s, and now the orange in our current era, we're using more of these kind of byproduct or secondary minerals for electronics, renewable energy, defense, automotive. And of course, the rare earth elements have been in the news because of China's kind of stranglehold on those around the compared to the other minerals or metals that are contained above. And so the notion is that maybe you can go into those historical tailings and find minerals that have been comminuted and use them today, when in the 1980s, we weren't concerned about concentrating them. And so option number one would be around those historical tailings. And I just say beneficiation or mineral processing, mineral concentration of old tailings. Those tailings have already been comminuted. They might be oxidized. They may need to be comminuted a little more if the desired mineral is very finely disseminated. But really, from that point, if it's deemed economic, it's a standard mineral processing flow sheet that could be considered. And so a good example of that current day is the fly ash. A lot of eastern coals have been found to have clay, and the clay contains rare earth elements. And so the Department of Energy's invested significant funding into the research and development of fly ash to recover rare earth elements. And the jury's still out on that, whether it can be done economically, but it's just an example of a potential source of some historical tailings. So option number two, and I'm not putting these options in terms of any priority list. It really depends on the tailings themselves. But I put up option number two, cement, here early in the list of options because we'll see that it's important for a number of other options. So what is Portland cement? Portland cement, somebody said at one point, you need 4 minerals. You need limestone, you need a lot of limestone, you need an iron ore, you need quartz, and you need kaolin. And in addition to that, you can put in a lot of different components, but basically for sure you need limestone as your source of calcium, and then you need a source of iron, silicon, and aluminum. These days, that fly ash, that product from coal combustion, is also a very common addition. So right there's a potential tailings addition into the cement mix. And like I said, it's become very common, and they're almost dependent upon fly ash at a lot of cement plants. That mix then is heated to prepare in a kiln to form what we call clinker cement. Mixed in with that is gypsum, which really slows down the curing of the cement, and it allows it to be stored and transported. And once it gets to the site, the clinker is broken up, aggregate is added, large sand type particles for strength. Fly ash can be also added at that point when the cement is wet and being cured. And fly ash at that point is what we would call a pozzolan, a natural mineral that enhances the cement action. So there's a couple places where a fly ash or maybe tailings themselves, if they're of the right chemistry, could be part of the cement making process. Then the water's added, the cement becomes workable, and with that larger aggregate becomes concrete. And so in terms of cement production, I'm showing a kiln on the left, and that it's fired at a temperature somewhere between 1300 to 1450 Celsius. I say beware of sulfides, right? If you have sulfides present, they're going to go out the stack as SO2. So probably tailings that contain sulfide minerals would not be a wise choice. And then I just list the chemicals that come from the cement process after after it goes through the kiln and becomes clinker. So it's a series of calcium silicon complexes that are necessary that make up kind of this magical paste that we call Portland cement. But so there's a need for minerals that contain calcium. That's almost always limestone. And then these others containing silicon, aluminum, and iron that some tailings might fit the bill and could be part of either that cement making process or might act as a pozzolan during the actual formation with water. So that's option number 2. Option number 3, I'll call bricks and related materials, or kind of construction materials. I'm a big fan of the U.S. Bureau of Mines, very nostalgic. They did a lot of really fundamental work for the mining industry. In 1971, there was a report of investigation that I found, dry pressed building bricks from copper mill tailings, which they took these copper tailings from different domestic locations in the United States, and they showed that you could make dry pressed bricks from the tailings. One of the drawbacks of that research, though, showed that you had to actually remove the pyrite from the tailings. Pyrite's a bad actor when making bricks because we're going to see that we're going to have to fire the material, and if you fire it above about 400 Celsius, SO2 comes off. So I think that was probably the biggest drawback to that research, was that you had to reprocess the tailings to get rid of the sulfides. And since you're producing a low value product, that extra processing step doesn't make a lot of sense. And so one of the things with traditional brick production, you want to avoid SO2, CO2 gas, and those come off at higher temperatures. Those gases, in case of SO2, obviously, is a bad actor, but they will cause cracking of the bricks, and since they're structural materials, that can't be tolerated. So what happens with brick making? Most bricks are made out of materials that are clay based, and that means they'll include clay minerals like kaolin that I mentioned earlier, and for sure quartz. Other common minerals in clays or clay-based ceramics include metal oxides, mica, feldspar, and the brick is formed by creating a mineral paste to form or shape the brick. It's allowed to air dry, giving what we call a green body, and then fired at a high temperature, generally over 1,000 degrees Celsius, to cause sintering between particles. And this graphic above is showing the sintering process. These are the individual starting particles in the green body. We go above 1,000 degrees Celsius, and the sintering process is a diffusion process between adjacent particles, and it happens at less than the melting temperature to give a consolidated body. And that is kind of described here and shown by this old graphic. A colleague of mine showed me this firing schedule, and I really like it because it goes through the temperatures and the reactivity of the minerals that are present. This is for a kaolin-based clay that includes quartz and mica. And at 1,000 degrees C, this chemical mullite begins to appear. Mullite is one of the desired constituents of ceramics because it has high insulating properties and it's very strong. And this sintering process then is occurring at temperatures less than the melting temperature because of atomic diffusion. And typically it will have fine particles less than about 200 microns. So it would contain those definitions earlier, sand, silt, and clay particles that are in close contacts. And the sharper the particles, the better in terms of getting sintering to occur. The final microstructure that results can be quite complex. Once again, depends on the starting material. But I think this rule of thumb that I found for brick is relevant to a lot of these tailings disposal methods where we're trying to add value. It's okay to add value, but if you're shipping bricks more than 500 miles, chances are you're going to lose money because you're shipping such a low value commodity. So that's something to keep in mind. Also, that the brick making is capital and energy intensive. That may dissuade people from making bricks with their tailings. Option 4 is paste backfill, or sometimes it's called cemented paste backfill, and it involves taking the mill tailings to serve as a reinforcement for underground mining cavities. And this really emerged in about the 1990s, just as a new technology for tailings disposal. Here, the flocculated tailings and some chemical additions are typically about 70 to 85% water, with water representing about 15 to 30% of the paste. Now, if you meet those guidelines, the paste is not what we describe as a non-Newtonian fluid. It needs to be pumped around. Common addition to the paste include our friend cement and a chemical addition called a plasticizer. And so that cement addition is typically in the 3 to 7 weight percent. It will serve as a final binder after curing and give structural integrity to the filled cavity. Where you're trying to avoid liquefaction if you can. One of the nice things, if it's sulfide mill tailings, you've kind of encapsulated the sulfides in this paste and it cures, and the sulfides are essentially completely encapsulated and controlled. So the cement as a binder opens up then the need to add plasticizers to help control the rheology. So this paste can be pumped from the surface down underground. So the big cost is the amount of cement in this operation, and so much so that the cement accounts for 75 to 80%. It's been estimated 75 to 80% of the backfilling cost. And so you can lower that cost perhaps by adding one of these pozzolans that will enhance the cement chemistry. Fly ash, slags are often considered to reduce the amount of cement and the cost of creating the paste backfill. Other considerations include that control of the solid liquid ratio coming out of that thickener, control of particle size. And here's a rule of thumb I found, that at least 15% of the fines must be minus 20 microns down into the silt clay region. So if your tailings don't meet that, you may have to blend the system to include finer particles. But if there's excessive fines, your cement consumption is going to go up. So there's a lot of considerations in terms of producing the paste backfill, including capital costs around the paste plant and pumping. And this sort of technology is most easily implemented in greenfield operations because it allows you to simultaneously design the thickening and paste systems. If you try to retrofit the paste system onto an existing thickening system, that can be problematic. Option 5 is shotcrete. Shotcrete involves using dry ingredients, cement, sand, aggregates with compressed air and addition of water just before the mixture impacts a reinforced wall surface, typically with rebar. And so the shotcrete flows around the reinforced wall, cures in place to give the wall structural integrities. Tailings have been investigated to replace the fine aggregate component in the shotcrete. But once again, you have to worry about sulfides, particle size distribution. I found just a few references where shotcrete was being used. compared to, say, that paste backfill, which is much more common, it seems. Now, in the 2000s, there was a kind of a new technology brought on called dry stacking technology. And you can see there's very subtle differences here between the dry stacking and the paste backfill. But what really enabled the dry stacking was large-scale vacuum and pressure filters on the dewatered tailings, where you could reclaim a lot more of the water compared to thickening. They're quite accommodating, even very fine clay particles, and they'll produce a filter cake that might be 80 to 85 weight percent. And you'll start seeing this term percent saturation, basically how how compressed these bricks or filter cake are. Once produced, then they're transported either on conveyor or a truck and dry stacked in an above ground geotechnical support. There's a great picture I found from Chile, one of the leaders in dry stacking technology, Anglo-American, showing the dry stack tailings on the right image, where they're just used to sculpt the reclamation land. And typically on top of that, or there's a liner put down, of course, to make sure there isn't seepage into the groundwater. The dry stack tailings then, after they've been allowed to air dry, are covered with native soils and vegetation. Now, some operations use both dry stacking above and paste backfilling in underground operations. Other secondary options I found in the literature that seem to be kind of one-offs, not proof of concept shown, but not much done with it on a large scale. Extenders in paints, those were copper tailings. Pigments in paints to impart color, iron tailings. So-called stone paper, very fine ground calcium carbonate made into a high-end paper called stone paper. And so some of what keeps tailings from being used for some applications, now this is just my opinion completely, it's energy costs in terms of those high energy costs associated with a kiln and the cement or sintering of ceramics. Of course, transportation costs. If you're trying to transport low value commodities, that will keep some implementations from happening. Mine waste regulations. If you're going to go back in and reprocess tailings, immediately you're going to inherit all of the liability. And if it's a low value product, you may not want to do that. And I think just a lot of lack of innovation and awareness and options. And that's kind of where I'm headed next. I'm a big fan of bricks. I think they hold a lot of potential. Here, this is a historical note that I found that prior to 1900, brick plants were common along the Missouri River in the Black Hills region where we're from. They were producing local material, and as cheaper lumber became available, brick companies went away. And maybe it's time we reconsider some of these indigenous materials, produce them locally, and perhaps include tailings as part of that equation. A big challenge with brick processing, though, worldwide, coal is used to fire kilns. And so you'll see things that say bricks are dirty. Well, bricks aren't dirty, but when you use coal to fire the kilns, they do release a lot of carbon dioxide. And it's been estimated 1% of global emissions are coming from brick processing. And just a shameless plug, this is a senior design team last year that proved that you could build a solar powered kiln. You can see the solar panel, the kiln in the back. They were able to meet the goal of getting to 1,000 degrees in the kiln. So I think, the notion that you need to use coal to fire kilns maybe is an old one. Another option with bricks, and this is more futuristic, the thermal energy storage concept. There's a couple companies, Rondo Energy in particular, is trying to commercialize this technology. The bricks serve for thermal energy storage. During daylight hours, solar and wind can heat the water around the bricks. The bricks store the energy, and then in off hours, you can pull steam and heat to the customer. So maybe there's a more of a high-tech energy future to bricks. Another consideration is using indigenous and local materials. Here's an example of an indigenous material. These are tailings, but it's kind of a nuisance material. It's a shale. This is just behind the school here on our campus. You can see the shale has fairly large clumps. We've been taking that material, reprocessing as is. There's quartz, mica, montmorillonite clay. We can reprocess it. We can form bricks, as you can see from that shale, a 3D printed vase. And so I think 3D printing might be in the future of tailings as well. There's cement 3D printers. Why not use 3D printing of tailings and produce low-cost housing adjacent the mining operation, for example? Another consideration in Rapid City, we're kind of a very isolated geographically. We have no use for waste paper or glass. We've been taking paper and including it in the shale material to produce some of these products. It's a great binder, and it helps keep the clays together during that green body formation. Another consideration is so-called cold sintering. Over the last 15 years or so, there's been a lot of research done around this concept, primarily at Penn State, most notably. And the goal is really to reduce the sintering temperature. It isn't really cold. Usually it's less than 400 Celsius. The mechanism is different than the sintering that I talked about earlier. It's an incipient water that has to be present, but at those kind of intermediate temperature, 300 Celsius, within the presence of water and pressure, you can actually get materials to sinter. And we've shown proof of concept with this around a limestone fine material and that shale. The nice thing is at those temperatures, you're not going to off-gas CO2 and SO2, and your energy costs may go down significantly in the process. So that might be something that we'll see in the nearer term. And then finally, I've been looking at this company called Dwell Earth. They produce compressed earth blocks. They'll supply a kit to allow you to determine if your soil is amenable to producing compressed earth blocks. If your soil, could be tailings, is adequate, add 4 to 8% cement, blend it in, press the brick. Now this is at room temperature to produce these earthen bricks that they claim have great strength characteristics. Now, I don't know how well they would hold up under moisture, but that might be an option. You can see that the reoccurring theme of add a little cement and your life will be good. So in conclusion, I'd say mill tailings are both a tremendous waste product and has a tremendous potential resource. There's a lot of processing options available, highly dependent upon whether you have historical tailings, new tailings, greenfield operation. And I think there's a lot of future opportunities if we're just innovative around indigenous materials, secondary waste products, and cold sintering, and perhaps those earthen bricks. Some selected references I'd be happy to share. If people are interested, just shoot me an email. I'll get those to you. Some acknowledgments of the students that have worked on this. In particular, shout out to the first three there, Sam Kessinger, Jacob Peterson, Kat Donovan, are always entertaining, crazy ideas that we have around this topic. And happy to answer questions for the group if there are some.
Thank you so much, John.
Excellent presentation. You know, there's a wide variety of people that need to see this kind of stuff. You know, it's one thing to show it to all those process guys and other people, but man, you know, the basics of all these kind of options and how this works, it needs to be by, maybe not so much the public, but some of the politicians and many of the corporate heads of companies who seem to be extremely ignorant in these areas, but that I've noted to their face on many occasions, as it turns out. And I just, obviously, I've been working on a tailings deposit in your backyard for 35 years.
Right.
And, here we are. It certainly fits in your category of because of environmental regulations. Well, now there are companies like we found most recently they're insurance companies and they'll take the liability for the PRP to do the project. So, we had those guys all lined up in a recent attempt for Whitewood Creek tailings, and yet we couldn't put it together. So, what do you suppose people like us could do that happen to know of 1 million ounces of recoverable gold along a creek where arsenic and mercury is falling into the creek and polluting my Native American friends' water down on the res? What the hell can we do to push this along? You think maybe you should like sick a graduate student on it and look at the reprocessing options now that now the gold is this high, it's probably a different flow sheet.
That's
And
right.
I would be more than happy to volunteer my time to mentor one of your students to look at that. What do you think?
No, Jody, that's a good point, right? We're both familiar with the issue. I think, yeah, we should talk about a senior design team next year.
Deal. Yeah. Yeah.
Yeah.
And you can keep all the gold. I don't care.
No, yeah, let's do it.
I like it. Great. Okay. That was it. But anyway, excellent presentation. It just needs to get out there. What can be done to where this can be broadcast to a wider audience? I'm not that kind of guy, but something I don't know how you can volunteer. It's a little bit too technical for, local community things, but it's kind of in the middle and there's a whole lot of people who are making decisions and making regulations that do not understand what you just presented.
Thank you, Jody.
Yeah,
Appreciate
that's not the way it should be, my friend.
it.
All right. Thanks anyway. I like it.
All right, looks like we had a question from Debbie.
Hi, John. Really enjoyed your presentation. Wanted
Thank
just
you.
to make a few comments on the need or the possible opportunities to look at particularly gold tailings as a source of a couple of critical minerals that are essential for the military, mainly antimony and arsenic. As an exploration geologist, you look at those trace elements to help you find a gold deposit, but I think once you've found it, you don't pay much attention to it. So I'm not sure those homestake tailings are a really good example. Do we have any idea what the antimony content in those tailings would be? Certainly evaluating that and quantifying or characterizing the tailings would be in and of itself a pretty technically challenging task. But if it's something that the military really needs, then maybe the economics of it could be influenced by some participation of the federal government as opposed to the private sector taking it all on as, gee, can we do this and make a buck?
John, can I make a quick comment? Go to
Sure.
Bald Mill Tailings. They had to roast that material because it was so full of antimony. Bald Mountain Tailings in South Dakota.
Yeah, I mean, antimony is often a trace element associated with gold deposits. So that's not going to be a one-off situation.
And the short answer is on those the Grizzly Gulch is I don't know. And I'll leave it at that. If I say more than that, I'll get myself in trouble, but I don't know. And they're currently, Barrick monitors that site. It's a locked facility. I just happen to have a senior design team get access to it. But yeah, I don't know on those kind of secondary elements that we weren't worried about in 1977.
Right. I mean, there are a lot of epithermal gold deposits in Nevada where there is a close association between gold and arsenic and antimony. So, we have, it's going to be certainly, um, it should be easier to develop an antimony source from tailings than to potentially go out and find a new antimony deposit,
Yes,
if it even exists as a freestanding deposit as opposed to a byproduct of gold.
right.
Thank you so much, Debbie. I had a question for you. How do you think some of these potential tailing usages should be incorporated into, PEAs or pre-feasibility studies?
I don't know. But what I will say is if somebody were starting a greenfield operation today, a large greenfield operation where they knew they were going to produce tailings of a certain mineralogical content, I would say okay, start by thinking about taking those tailings and producing low-cost housing adjacent the mine site for the people, and you might have a better chance of attracting a workforce if you do that. But that doesn't answer your question, but that's how I would think, given where we are in terms of workforce needs, low cost housing needs. I think you could take that tailings component and help solve some of your other problems.
Yeah, great.
I'd just like to make a comment on that. There are some of us who've been trying to get upper management in mining companies to include legitimate and final closure costs in our PEAs and pre-feasibility studies, and we have not fared well until only the last few years. Uh, they always get killed by the accountants and the lawyers. It's pretty straightforward. And John hit it on the head that if you try to do that with something that's beneficial for the community, that's a great idea. And there, you know, I've tried that on a few projects, and so far I've been unsuccessful. Maybe because I told them they were idiots. I don't know.
Well, you might also add to that analysis the fact that tailings disposal and tailings impoundment they're controversial in a permitting
Right.
dialogue. So if you could develop a redevelopment of the tailings into something else, it might lower the level of opposition and concerns about the long-term stability of a tailings disposal facility.
Mm-hmm.
You are exactly right.
Well, with that, many thanks to John for his excellent presentation, and thank you to all who attended our webinar. All of our webinars are uploaded to YouTube and can be accessed through the MMSA.net website. The video of this webinar should be on the website within a week. We will post on our LinkedIn pages when the video and slides are posted to the website. Our next webinar will be on December 12th, slightly early due to the holiday season, by Corey Milburn and Mark Nichols on an introduction to construction claims. What are construction claims and why do they occur? We will post the PR for this next week on our website, LinkedIn, and Eventbrite. The MMSA webinars are supported by the MMSA Jacqueline Foundation. Again, if you are interested in becoming an MMSA member, please be sure to check out our website at mmsa.net for information on the application process. The webinar is now ended. Thank you.
Thank you all.